Now let's talk about photosynthesis and the process of building organic matter in the plants, and again the connection with climate and climate change. Well, if we look at how plants interact with, say, carbon dioxide and moisture, a lot of this happens through tiny little holes we have on the underside of leaves. We can see here in this image below these holes, which this is actually flipping the leaf upside down. Tiny holes we call stomata, and these stomata can actually open and close to allow greenhouse gases in, allow carbon dioxide in, allows the water to leave. And this is where a lot of the things are happening on the plant in the stomata. The water in the plant is actually taken up from the surface through the roots. The water in the surface extracted from the soil, but it gets taken up to the leaves, and about 99% of the loss of water from the plants occurs through these little holes, these stomata on the plant leaves. And we can see this little diagram at the top of the stomata when we have a very swollen, open stomata, which is in very good conditions, compared where we have a shrunken stomata. And plants know how to open and close these stomata based on the climate conditions. And on the bottom right, we can see that basically the production of organic matter, of glucose, is basically the photosynthesis process takes up light. We need water, we need carbon dioxide, which comes in through the stomata to produce the organic matter that we have in plants. So if we look at how the plants and the stomata react to changes in the climate, we can also call this the stomatal resistance. It's resisting various factors in the climate. In the top, we can see basically that the stomata will open up when we have optimal conditions for growing, when we have high light levels, we have moist leaves, we have warm temperatures, moist air, moderate carbon dioxide, and high leaf nitrogen. But when the opposite is true, the plants know to close the stomata to conserve basically their energy and their water. For example, when we have low light levels or dry leaves, cool temperatures, the air's dry outside, even high levels, when they're too high and they don't need all the carbon dioxide, when we have high levels of carbon dioxide, plants can also close their stomata, and when we have low nitrogen content. So the plants again can modulate and regulate their resistance and open and closing depending on the situation in the environment around it. Now, it turns out when we look at historical data and fossil data of plants, that in warmer climates, when there's a lot of carbon dioxide in the atmosphere, plants actually developed fewer stomata. So there were less of these little tiny holes on leaves because they didn't need so many stomata for photosynthesis. And we had fewer stomata when we had warmer climates in the past for the same plants, and more stomata when we had colder climates. So plants know how to evolve and adapt to changes in the climate if they have enough time. And that's the big question, if they have enough time to develop. But when we do have, say, temporarily warm climate or drought conditions, plants know how to close the stomata to conserve that water so that they don't lose it into the environment. And so there is always this dynamic interaction between the stomata, when they're open and closed, and the condition in the air around the plants. So the process of actually producing organic matter, we can see the equation here. We need water, we need carbon dioxide, and we need energy, which is the sunlight. And this will produce organic matter, which we can see generally written as carbon together with the water molecules in different types of carbon structures. And the plants give off oxygen into the atmosphere as a result of this process of photosynthesis. The opposite occurs when the organic matter eventually dies, say at the end of the summer, at the winter, when we have decay of organic matter, also in garbage dumps, and we'll go in the opposite direction. The oxygen in the air will react with the organic matter and will give off carbon dioxide and water and even heat back into the atmosphere. So photosynthesis takes up the carbon dioxide, but respiration and the decay of organic matter will return that carbon dioxide to the atmosphere. The process for very thin leaves. This process of carbon dioxide and decay, take-up of carbon dioxide, and the return happen fairly quickly for very thin, fine fuels like leaves and small branches and grasses. But when we're talking about huge logs and huge trees, this can take centuries of, first of all, taking up all this carbon dioxide, and eventually these trees can even be buried in the ground for thousands of years. Eventually they may even form coal and oil, which then when we burn it once again, which we're doing today, we release this carbon dioxide back into the atmosphere. So the biosphere actually acts like a huge bank of carbon. It's taking up carbon dioxide from the atmosphere, storing it in the big logs in the trees all around the world in the forests, and we can keep that carbon there for hundreds, thousands of years if we don't get rid of that tree and if we don't burn that biomass and return the carbon dioxide to the atmosphere. So there are actually a few ways that we can do photosynthesis, and I'm not a biologist, I'm not an expert, so I'll just point out that you should know that there are basically two primary photosynthetic pathways in plants. We call these C3 plants and C4 plants. You can see kind of this diagram showing the actual physical differences in the structure, but the differences are actually how these plants produce organic matter in the photosynthesis. And for some examples, you can see C3 plants are basically like apple trees, barley, grapes, oranges, whereas C4 plants are things like corn or maize, sugarcane, and it's related to how they actually fix the carbon in the plants. And if we look on the left, for example, the C3 plants, they use what's called 3-carbon organic intermediate stages to fix the carbon, and this is about more than 85% of all the plants fix carbon in this pathway of the C3 plants. A lot less plants in the C4 plants. We can see in the middle panel, like corn, and this is mainly in the subtropical, the tropical grasslands, and only one tree, there's only one tree found in Hawaii, for example, that fixes carbon in this pathway, the C4. So the majority are C3 plants. And just to also point out that we also have a third category, which is these CAM plants at the bottom, which are really the desert plants, the succulents, which have a different pathway of fixing carbon. But since this is less relevant to climate change and less biomass actually in these environments, we won't talk about that anymore. But the photosynthesis of the C4 plants is much more rapid, about 6 times faster than the C3 plants. We know that grasslands, for example, grow very quickly. Grasslands and corn from vegetation, sugarcane, grow very quickly compared with apple trees or orange trees or other forests. And so the rate of photosynthesis is much faster in the C4 plants. Well, what's going to happen in the future if we increase carbon dioxide? So some people say, hey, this is great. If we have more carbon dioxide, we're going to have more plants, we'll have more vegetation. This can have a cooling effect in our cities. It's many positive issues of having more plants. And so if we look at some experiments which have been done to see what happens in the laboratory when we increase carbon dioxide, we can see here that the blue points on this curve show the photosynthesis rate, which does increase when we have more carbon dioxide. So we're at the moment around about 415, 420 ppm in the atmosphere, and but we do see this kind of reaches some saturation point that it doesn't keep on increasing the photosynthesis rate forever. Eventually, it kind of reaches a maximum and flattens out the curve. And the green curve shows the transpiration rate, that as we have more carbon dioxide, the loss of water actually decreases as well. So this seems to be good. And if we have more carbon dioxide, then we have more vegetation, less transpiration. And if we look on the right-hand side in the table, this does seem to be the case for many types of plants, both C3 and C4. And this is going to extreme cases of, say, 600 ppm and going up to 1200 ppm. The two left-hand columns show the changes on the photosynthesis rate, and the two right-hand columns are for the actual amount of biomass we have. And we see that it does increase as we increase CO2, but not for all plants. If you look in the orange boxes here, we can see some plants actually have an opposite effect. We have a decrease in the rate of photosynthesis, and we have a decrease in the biomass while we're increasing the CO2. But I should point out that all of these experiments are done with all other parameters being held fixed. And other parameters which are going to change in the future are temperature. It's going to get warmer, and we're going to maybe have less water and maybe less nutrients in the soil. And so by looking at these experiments, we have to also be careful coming to conclusions, because this is only the effect of the CO2 fertilization. But if we take into account other parameters, we may not get the same results. And if we look at this example, which is taking into account also the respiration and the impact of temperature, again, first of all, on the top, we can see how photosynthesis rate will increase as we go from low carbon dioxide to high carbon dioxide. But it's slightly different for the different types of plants, the C3 and C4. But already at the values we have today, above 400 ppm, we can see that the C4 plants are not going to increase anymore. We've reached this kind of plateau, and it doesn't matter how much more carbon dioxide we put in the atmosphere, it's not going to increase anymore the photosynthesis rate. But at the bottom, we can also see the impact of temperature. On the bottom left, we can see the CO2 flux, which is taken up by the plants just by photosynthesis, shown by the green curve, and the respiration, which is the loss of carbon dioxide, we can see by the red curve. And we see that when we put these two together, there's an optimal temperature around about 25 degrees where we have the maximum uptake of carbon dioxide. If it's too cold, if it's too warm, we have less carbon dioxide taken up by the plants. And so when we take into account also temperature, we see that if we keep on increasing carbon dioxide, but the temperature also goes up, this is going to have a negative effect on the uptake of carbon by the biosphere. And in this animation, which we may have seen before, we can actually see the annual cycle of the carbon dioxide in the atmosphere because, and you can see this in the background, the growth of vegetation both in the ocean and on the land, what we call the breathing of the planet. As we increase in the spring the growth of leaves and new trees and new vegetation, we have a decrease in the carbon dioxide in the atmosphere. It's taken up by the plants. When the plants die in the winter, it's returned back to the atmosphere. So we see this up and down every year due to the biosphere. But we also see this increasing trend, which when we again put this in the perspective of the last 1,000 years, we see that something very strange is happening. The global trend of the increase in greenhouse gases, the carbon dioxide in this case, is because of man-made activity on the planet and the burning of fossil fuels. But the fine details, the up and down of the cycle we're seeing every year, is due to the photosynthesis and the respiration of the plants on an annual basis.